Okay, so welcome everybody to this other Thursdays of seminars here at BrIAS. It is really my pleasure to introduce our first speaker, who's Denis Dochain from UCL. So Denis is one of the most well-known control guys here in Belgium, so I'm not going to make the list of everything that he has done and all the many achievements he has done, because otherwise we are spending a lot of time and then I'm reducing the time for which he will speak, and I'm sure he will present a lot of interesting things. So it's really my pleasure to introduce him, and I leave him the stage. Thank you, Denis, for coming.
Thank you very much, Emmanuel. Do you hear me without the microphone? Is it okay? No. So I shall use this microphone. My voice is not very loud, so I probably need a microphone.
No, it cannot move a lot. It cannot move a lot because you have recorded.
Oh, so I have to stay here? Is that? Yep. Okay, good. I'll do my best. You know, it's not my temper to remain just fixed on the floor. Anyway, I'll do my best. So please tell me if you believe that I'm not doing it correctly. Should be okay. Yes. So my presentation today is about adaptive control of reaction system. And so maybe I need to tell you about what is a reaction system. So reaction system is any system when you have transformation of matter. So this applies in a number of fields. So biological systems, and indeed this includes also metabolic engineering or synthetic biology, if you prefer. I mean, all these terms tends to evolve in time, but this typically is the way that you look inside the cells. Chemical systems is another type of reaction system. Environmental system, and I use here the example of wastewater treatment, which is one of my favorite type of application. Ecological system, and this include microbial ecology, the fact that you have, let's say, interaction of between different species in biology, and also this include all these, topics related to epidemiology. So the SRR model is nothing but a classical, let's say, ecological model. Indeed, it was one of my surprise when the, let's say, the COVID crisis came, that so many people, start to work on controlling, epidemiology. But then I was really surprised that most people tend to reinvent the wheel, because all they were touching this was stuff that were known by a lot of people, including me. But anyway, that was great, and so this means that also this is a nice type of application of reaction system in the large sense. And I'd like to mention also plant growth, which was one of my favorite topics. So a plant is clearly a biological system, but not as microbes, but then it's an important biological system, and therefore it is a reaction system. Okay, so what is important to understand, what is different from reaction system with any other dynamical system that we consider in automatic control? First of all the variables, these are concentration, temperature, quantities in ecology, for instance, these are positive variables, okay? In mechanical engineering, you have, let's say, position or velocity. These can be positive, negative, whatsoever, but this is not the case here. These are all positive. Energy that you have are not quadratic functions. And it's because, in some sense, it's fundamentals of the thermodynamics in this case that related to this kind of reaction system. It's really related to the fact that the properties don't need to come with, let's say, square values of variables to come with energy. Dynamical models, typically dynamical models comes from fundamental, let's say, balances, mass energy balances, and sometimes momentum balances, which is probably also very typical from what we have in reaction systems. On top of that, most of the model, 99% of the model are nonlinear, but also with a large uncertainty on the parameters. And also there's a lack of accessibility to many important variables. in many instances, or for any of the example that I mentioned before, it's very difficult to get, let's say, online, precise measurement, reliable measurements of, let's say, the variables that are important for the dynamics of the system. Okay, so I would like to start with what I call general dynamical model, then move to what I would call two key properties of any reaction system, and then I will deal with state and parameters estimation and then adaptive control. Okay, so what I say is that this equation, which is, say, a matrix equation, is a general way to look at any reaction system in a confined medium. Okay, confined medium means that you have, let's say, the fact that, let's say, the system is homogeneous. But in that case, but you can, let's say, consider, let's say, variation of that, but typically this is always the same. Always the same. The first, let's say, element is the fact it is the transformation of matter, okay? So typically, Kr of x is the multiplication of matrix, which is in chemical engineering known as a yield coefficient matrix, stoichiometric coefficient matrix, and in bio, or in any other case, it's a yield coefficient matrix. And R of x is a reaction rate, is let's say, the rate at which a transformation takes place. And all the other terms is the fact that the medium is not closed. So if it's closed, you don't have that term. If it's not closed, then you have, let's say, the interaction with the environment. So F is the feed rate, so what you put inside the medium, minus Q is the term of, let's say, gas that may go off of the medium. And the last term is called typically the dilution rates, but it is the quantity of matter that leaves the medium. Okay, so this is typically transport dynamics. Okay, so lowercase q is typically a volumetric flow rate, and V is the volume. And having said that, I have everything to go ahead. So let me take a first example, anaerobic digestion, which is a wastewater treatment. Well, it's a long wastewater treatment, I mean, known for let's say, centuries. And so it has the advantage to produce methane. So it was very popular at some point, let's say, typically with the first oil crisis in the 70s, because people say, oh, no, we found an option, an alternative to produce energy, let's say, without oil. Anyway, so this is a long story. But then this process, is a very complex process. You have, in bio, they say this is an open medium. This means that you have a lot of different species, a lot of different bacteria, if you prefer, that interact. And when I say a lot, it can be thousands, okay? But there's one way to look at simply is that to consider that typically you have only two populations. And so this is what I say, in this case, a simplified reaction scheme. So I have a first step, which is called acidogenesis, when you transform the organic matter that you want to degrade by acidogenic bacteria into volatile fatty acids. And these volatile fatty acids are then degraded to produce methane and CO2 at the same time, but this is done with methanogenic bacteria. So if I consider that, my model will be written as follows. I have mass balances for, let's say, the acidogenesis, so the first two elements in my first reaction, and then the second step, when I have look at, for instance, which is interesting is to see here, this is volatile fatty acids. It is produced by the first reaction, consumed by the second. Okay, so this is very simple. This is mass balances, very 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 easy to note. So okay, so in this case, I use the notation, classical notation of bio, which I say that I have D, which is the dilution rate, which is nothing but the ratio of Q over V. And so if I want to put that in my general dynamical model, it's very simple. I just have to define typically my, let's say, state vector here with all the components in the reactions. And I have to define my yield coefficient or my stoichiometric coefficient matrix. Okay? So for instance, if I look, so each column corresponds to each reaction, and each row corresponds to let's say the intervention of one component in each reaction. For instance, if I look at this one, volatile fatty acid is produced by the first one, is plus K3, and is consumed by the second, is minus K2. Very simple. And it's completely general. So what is interesting in that case is that for bio, if we have bacteria typically the reaction rate is the product of what is called the specific growth rates and the concentration of the bacteria involved in the mechanism. So this is known as an autocatalyst. Okay, so you need the biomass to have the reaction, but the biomass at the same time is produced by the reaction. So that's why it is not just a catalyst, which is quite known by chemical engineers, but it's an autocatalyst. Okay. Okay. Anyway, this is a word that you could keep in mind if you wish. But of course, let's say the issue in that case is that what can I put in mu? Is mu just a parameter? No, it has to depend on the system variable. And for instance, you know that you don't have anything to eat, you will not grow. This is exactly what this curve shows. The more I eat, the more I grow. And this is known as the mono model in that case. But then you can have indigestion. Okay, you eat too much, you get sick. And this is this term. So this function is monotonic, and this one is non-monotonic. And so when you reach some maximum at some point, then you have decrease. So the fact that you have decrease of the growth by that time. Okay, and then you can have a lot of other dependencies. For instance, you know that one type of microorganism will be active in a specific range of temperature. Okay, fine. So let me look. So I look at the bio. So let me look at the chemical example. So in that case, typically, what is a matter of, let's say, issue for control is the fact that you have a reaction that can explode, if you wish, okay? And this is typically known as non-isothermal exothermic reaction. So when let's say the reaction enthalpy might be negative in that case, and so then this can be a source of problem when you want to control it. So typically, what is different between the example that I've shown before is not let's say the energy takes place, okay? And so the energy balance can be expressed in terms of temperature, which is a variable which is rather easy to measure, okay? So in that case, I can rewrite my model also in my general dynamical model by considering that T is one process component. Okay. Let me move to a third example. It's a ecology example, the famous prey-predator model, okay, where you have, let's say, a mass balance for the prey, when you have a growth rate and a constant term by the predator, and for the predator, that's the production by consuming the prey, and then you have a mortality rate, okay? Okay, this is this is exactly what I would have in that case in the general dynamical model. Once again, it fits in the general dynamical model. Okay, and this is a great, example. I could tell you for long about that model because there's so many nice properties, and the fact that it's periodic. You know that. If you are a little bit aware of that, with that model, it was the idea that it was able to emphasize the fact that typically when you have a lot of prey, then it tends to let's say, move to an increase of the predator. They have a lot to eat, but then the number of prey decreases, and then the predator don't have to eat anymore, so they decrease, and at the same time it's a kind of a periodic, let's say, a behavior, which is observed, let's say, a lot in nature. Okay, so now I have my basis, I have my model, and I can start working, okay? But I want to do more, because I want to see what can I do? Can I take advantage of the fact that this reaction system, they have some specificities? And so that's what I would like to mention, is that reaction invariance and slow fast dynamics. So the notion of reaction invariant is very well known by chemical engineering in general, and chemists also at the same time. It's the fact that when you have a reaction A given B, this means that the number of moles of B that I produce are exactly connected to the number of A that I consumed. Okay, that's a constraint. So in mathematical sense, this means that there is a mathematical constraint somewhere. So typically when you have a system which is closed with no exchange with the environment, in that case, this is a true mathematical invariant. Okay? This is exactly what I show here. So there's a general properties, so I can make a state partition, XA, XB, such that the some matrix KA related to XA is full rank. And then the property is general. The property is that I can define a variable Z, which is a linear combination of XA and XB, where A0 is the solution of this matrix equation, in that case. And then in that case, I can rewrite the dynamics for XA and Z, and it is completely equivalent. So these terms are only related, so independent of the kinetics, or the transformation, let's say. And in that case, you know, these terms, which are typically transport dynamic only, if the system is closed, this must be equal to 0. That's what I said just before. This is exactly the fact that in that case, it is a mathematical invariant. Okay, and this is a very strong property. And so the idea, I mean, can we use that for control? Second property is what I like to call slow fast dynamics, often mentioned as singular perturbation, but I like the way this slow fast dynamics. And so it ends up to come up with a very well-known approximation in chemical engineering, which is called the quasi-steady state approximation. So let me try to explain, or I can come up with that. Assume that I have a sequence of reaction, A1 given A2 given A3. And I assume that the first one is slow and the last one is fast. And these are the reaction rate related to each reaction, okay? And I assume that at least, so K01, K02 are kinetic constants, but they have to be such that the reaction rate must be equal to 0 if there is no reactant, okay? If I have no A1, I cannot have the reaction A1 given A2, okay? That's simply that, and that's why I put this here, okay? Okay, and so intuitively, I mean, if you are engineers and even if you're not a chemical engineer, you will understand that very easily. If this reaction is slow and this one is fast, this means that any time that I produce 1 mole of A2, it is directly transformed into A3. So it's like having one reaction, A1 given A3, okay? And so, okay, so how can I come up with that conclusion? So I define a small parameter, which is the inverse of the kinetic constant KO2. And I rewrite my dynamical mass balance for A2, so the concentration of A2, pre-multiplied by epsilon. And so I put epsilon to 0, and then I obtain this algebraic equation. And since typically I assume that this, generally speaking, this term phi has to be different from 0, the only option is that the concentration of A2 is equal to 0. Okay? Second step, I make let's say the mass balance for the sum of A2 and A3. I come up with this equation, but so this becomes the mass balance equation for CA3 because CA2 is equal to 0. And so this is done, because typically I say that A3 is produced by the first reaction. Okay? Simply as that. Fine, so I can come up, let's say, with a general rule with respect to that. But then what is interesting is that, for instance, if you look at metabolic engineering, this property is very largely used too. Okay, it's a very common, let's say, assumption that it's used. The quasi-steady state approximation that I justify here is very common in metabolic engineering. So I try to make the connection with every field that I mentioned before. Okay, let's move to state observer. And then I would like to say I can use my reaction invariant. My reaction invariant says that I can write the dynamics of the system, part of the dynamics, independently of the kinetics, which is an issue because I mentioned that I have a number of models, let's say typically for the reaction rate, but all these models, they are typically, let's say, heuristic. There's no fundamental model, let's say, used in practice for kinetic model. So in that case, so this is an issue. I would like to have a state observer which is in some way insensitive to the knowledge of the kinetic modeling. Okay, and so now I make another partition when I put x into x1 what I measure and x2 what I do not measure. I rewrite my z that I mentioned before as a linear combination of x1 and x2, okay? And I have to make sure that I can invert A2 in that case. And so in some cases, it's just a left inverse, but it's a classical inverse in most cases. And so then what I do, I compute z from the equation that I mentioned just before, and then I invert this relation just to get, let's say, an estimate of the variable that I do not measure. And this is an observer, even if I don't have, as a classical observer, if I don't have correction term, this is an observer. Because I can guarantee, that's why we call it an asymptotic observer, we can guarantee the convergence. And the guarantee of convergence is related to this condition, which is very classical in adaptive control, which is called the persistence of excitation condition. So I can guarantee that as long as the dilution term, let's say the flow rate, if you prefer, is not equal to 0 for too long, then I'm pretty sure that the estimation of the x2 add will converge to x2. Okay, so the estimation of my unknown state will converge to the true value. Okay, application. So ETBE, so ethyl tertiobutylate ether, is an additive or unadded fuel. So this is the case when we have what we call a fixed bed reactor in that case. And so the reaction is typically transformation of ethanol and isobutene ETBE. Its non-isothermal is exothermic because it's minus 40. The process, so I mentioned it. So what we measure is the temperature at 4 locations. Okay, these are the 4 locations. So inlet, outlet, and 2 positions in the reactor. And also measure, let's say, the concentration via an HPLC at the output of the reactor. So these are typically the measurement that we have in that case, the temperatures typically, and let's say typically the concentration in that case. And so this is typically what we obtain in terms of estimation. So as you can see, I have a quite good fit, let's say, of the different variables in that case. Okay, online parameter estimation. So as I mentioned, that there might be a lot of uncertainty, typically on the parameters in the model. So probably need tools to, let's say, be able to reconstruct, let's say, the parameter online. And so I go back to my general dynamical model. I assume that, let's say, the reaction rate are partially known. Okay, so this is the unknown part, this is the known part. Okay, and I rewrite my dynamical model as follows. So if I do that, and I assume that I have a number of measured or observed component which is equal to the dimension of the matrix H, which is here. Okay. And so I just use, let's say, classical observer-based estimator, so with this correction term related to the states in that case. And so classical parameter design, omega, gamma. I know that typically I have this kind of rules. I can do that, it works. But we found one way which is much better than that, which is very easy. So we say we can use a transformation, an auto transformation in that case, when I have zeta, which is the inverse of the submatrix K, U, multiplied by the state vector, okay? And then, so if I use that, this is how I can rewrite the equation, but it happens that in that case, because of this transformation, if I do that, I can rewrite my, let's say, observer on a basis of 2 by 2 equations. So one estimation is related to one measurement, or more precisely, one combination of measurements. Okay, and then in that case, it's very easy to calibrate, because I have only a system of order 2, which is very easy to calibrate. This is exactly what we have in that case. So we found a way to get very simple way to calibrate the system, and a calibration that can be different for each parameter that you want to follow. Because in that case, typically what you have to follow is not constant parameter, but parameter that might change with time. Okay, so that's why I would like to illustrate that in the next slide. So application now is animal cell culture, so which is also very well used in pharmaceutical, let's say, applications. So in that case, we have, let's say, reactions came with 2 reactions. Glucose is in both cases. In one case, you only grow biomass, let's say it's called respiration, because you have oxygen, okay? And then in the second case, you produce lactate, okay? And that's interesting. So this is different from what I did before. We have a fed batch reactor. What is a fed batch reactor? In a fed batch reactor, let's say you fill partially the tank, and then you introduce matter progressively until the tank is full. Okay, so that's why it calls fed. So the first phase is fed. I'm feeding it, and then when it's full, then I wait for the reaction to be completed. So this is what is called batch. So what is called fed batch, and that's very interesting, because you don't have steady state in that case. There's no steady state. The steady state is at the end, and when there's nothing to be consumed anymore. So this is a kind of system that which always in dynamical situation, which is very different from what we have in many cases in other automatic control application. So we measure glucose and lactate plus some offline measurement of biomass, and we like to estimate the 2 specific growth rates. So that's very interesting. So the measurements are at the top, okay? These are the 2 mu that I would like to estimate. So if you look at the 2 mu, the 2 specific growth rate, they have a completely different behavior, okay? So that's what we need, some tools to calibrate differently, so we can make that independently. This is great. And what we did, the challenge was to make sure that we could fit. So the circle here are the offline data. Okay, I use at some point some asymptotic observer. This is the red line, and the green line is the validation. What is the validation? This is a crazy exercise. In that case, so is a completely unstable system. So you try to compute the mass balance equation for the biomass in that case, but just putting the value of the estimation of u on the 2 mu's. And if you look at these equations, the equations are unstable. So if you make a slight difference in the calibration parameters, the estimation explodes. So this is really a very interesting exercise in that, and very important in that case. Okay. So if you want to interested by that type of let's say kind of results, this is the result that I obtained a few years ago with Romeo Ortega and co-workers. Let's say on extending, let's say, the result that I mentioned just before. Let's move to adaptive control. So. And so typically adaptive linearizing control in that case, the fact that the model is typically nonlinear, so we have to find some way to handle the nonlinearity, and at the same time, since there's a lot of uncertainty, it might be good to make sure that we can adapt the controller to the let's say the changing behavior of the system. So typically, if I want to write it in a general way, I can write the dynamics of the output that I want to control that way. And so this is typically done by using my slow, fast, let's say, dynamic reduction, okay? And typically, I need to have all these terms. So I typically need to have a reaction term somewhere. If I have gas, that's important because it's easy to measure, so it's probably important to have it in my equation. And then I need also the fact that I feed, let's say, the system by some, let's say, reactant or external, let's say, external feed. Okay, so very simple way. I want to have, so it is a first order, let's say, differential equation. I say I want to have first order dynamics in that case. Oops. I combine the two, and I typically have my control, let's say, equation. If I decide that the flow rate is my input in that case, which is really standard, let's say, in any case in reaction system. And so since I have, let's say, uncertainties on the parameter, I typically have to estimate alpha, beta, and gamma, and the reaction rate, which might be a sort of uncertainty too. Okay? So let me show you a simple example. I go back to my anaerobic digestion example that I've shown at the beginning. And so in that case, I mentioned volatile fatty acids, and if you are not chemical engineering, this is something that you don't know what it is, and I don't ask you to know what it is. What you have to understand in this kind of systems, volatile fatty acids is a source of instability. So typically, at some point, what you may have is what they call accumulation of volatile fatty acids. And so when you have a lot of volatile fatty acids, they tend to inhibit the growth of the methanogenic bacteria. Remember that I show you what I call the indigestion model, aldane model, which is a non-monotonic function. Okay? So typically, this can be represented by that. So if there are too much, let's say, volatile fatty acids, methanogenic bacteria cannot grow anymore, and so you don't produce methane anymore. And then typically what's happening, typically they have what they call a washout. So typically the growth does not compensate let's say the dilution. So at some point you have no more methanogenic bacteria in the system. So this is something that people that and manage, let's say, anaerobic digester want to have to make sure to guarantee at least the stability of the system. So avoiding accumulation of volatile fatty acid, avoiding instability. Okay. So typically, okay, we assume in that case that methanization is a limiting step. Okay. So in that case, we may have accumulation of volatile fatty acids, and so typically we use the slow fast, let's say, reduction that I mentioned before, by assuming that methane is a low solubility product and the acidogenesis is a fast reaction. And then this is exactly the algebraic equation that I obtained in that case. And so typically I can rewrite the dynamics of, let's say, the volatile fatty acids by using this reduction as follows. So this is the model that I can use in that case. Okay? Use that I have the inlet of organic matter concentration here, and I have the methane gas flow rate here. Okay? And this is typically an example that we have in that case. So typically, if you see, where is it? Too fast. In that case, you see that the control works well for the volatile fatty acids. Okay? These are the results of a European project that it was called Amoco that I had quite a while ago. Okay, and then, okay, we can do one step further. Okay, so is it possible to get to optimal operating points without knowing what is the operating point? So once again, a lot of uncertainty about the system. But we know that so on paper we know, and we know from practice that there is an optimum somewhere. Okay? And that's really the job of adaptive extremum seeking. So you do control at the same time that you do optimization. Okay? I mean, in chemical engineering, people tend to call that real-time optimization. Okay, but that's simply adaptive extremum seeking. So this is adaptive control, but at the same time, the adaptation is related to the fact that you are looking for the optimum in closed loop. Okay? And so there are a number of, let's say, I mean, I have a lot of results on that, but then there are typically two types of situations. One, the model structure is fully known, and one is which is partially known. I just use an example for the second part. So once again, I go back to a simple example, okay? One biomass, one substrate, and one product. So this is the equation that we have obtained by model reduction, and we assume that we have a mono equation in that case. So we don't know the parameters of the mono model in that case, and for, let's say, but this is not a strong assumption. For let's say, convergence analysis, we need to assume that this term is bounded. And we assume that we measure the gas flow rate and we measure the substrate concentration S. So what we do, we define three new parameters, theta mu, theta S, theta K, and we write the dynamics of the system as follows. So we compute, let's say time derivative for y, which is exactly what we have here. Note that we have this at the denominator, okay, which will be interesting to understand. So if I want to make sure that I have an optimal point, I compute, let's say, twice the derivative of y with respect to s, okay? You see this term is strictly negative, and you see that there's an optimum if this term is equal to 0, okay? So the optimum is for the concentration of substrate which is equal to this value, okay? And so this is, two steps. First step is the parameter estimation. Once again, this kind of, let's say, classical observer-based estimator, okay? And so the parameters are in the two equations here, and I update the parameters by using this, except that I also use a projection algorithm in that case to avoid to have a division by 0. So since I have this term here, it might happen that this term becomes negative, and so this might be equal to 0. So we use a projection algorithm to avoid, let's say, division by 0, typically. And so, let's say the control law looks like, if I look, is let's say, kind of an extended version of the adaptive generalizing control that I mentioned before, except that I have this term, and I have a term which is d and d dot, which is called as the data signal, or let's say the excitation signal if you prefer, okay, in that case. And so this is my control error, but with the data signal also at the same time, okay. And so if I want to look at the convergence of this, I have this Lyapunov function, and so remember that I have this term somewhere at the denominator in my equation for y, okay? So this is probably one of the nice tricks in this case. So this is classical. I have a term which is the square of the control error, terms which are related to the square of the error in the parameter estimation, and then two terms which are related to the estimation of, let's say, the observer base part of the parameter estimation, okay? And so it's easy to show that in that case, I have this value for the time derivative of v. Typically, I can invoke the Lassalle-Yoshizawa theorem and the Lassalle invariance principle to show that what I have is that, I will converge close enough to the optimum in that case, which is exactly the result that I have here. So typically, these terms are related to the external excitation or the data signal, if you prefer. So if this term will tend to 0, if my data signal and its time derivative will tend to 0. So in that case, I can show that I converge to the optimum without knowing the optimum. Okay, that's the idea of adaptive extremum seeking. Just a few simulation. So note that in that case, because it is a maximum, it's impossible to move up over it. Okay, we are always below it. Okay, but then this is exactly what we have: the convergence of the parameter in that case, and the fact that if we remove the data signal, it will tend exactly. So it can remain close enough to the optimum. Then if I remove the data signal, it will tend to the optimum. Okay. Parameter in that case, in this case. So a lot of possible, let's say, extension of that. This is an extension for chemical reactors. Remember that I have the concentration of the different reactant products, the temperature here, and in that case, typically what we want to, we know that there is an optimum in that case, typically when I have sequence of reaction, which is the case here, A, B, and C, which is indeed the part of the what is called the Van der Waals reactor. So we start, so the optimum is somewhere here. We start from nowhere, if I may say it like this, and you see that it converges to the optimum. Okay, so I'm at the end of my presentation, so I would like to thank you very much for your attention, and I'll be happy to answer any question. And before that, I'd like to put that in your agenda. In 2 years from now, we are going to have, let's say, the ECC here in Brussels, but on the UC Louvain site in Woluwe. So thank you very much, and I'll be happy to answer any question that you may have.
So time for questions. Alejandro, I know you want to make some question.
Well, since I have the floor, thanks Denis for an amazing presentation. Similarly, Emanuele wants a question from my chemical viewpoint. I was wondering, when you are talking about water treatment, you mentioned digestion in this case, but when you mix processes like digestion and also with the removal of nitrates, and also phosphates, you have an interplay between two different time constants over a long process. So in that case, it's better to decouple the chemical reactions, to treat them all together, or what would you do in that case? I mean, let's say digestion depends on the amount of oxygen that you are injecting to the reactor, while the removal of nitrates and nitrates depends on the quantity of organic matter that you still have, because it's an oxic product, but you don't have a lot of oxygen, for instance. No,
but what you mentioned is another type of process, wastewater treatment. So this one is anaerobic digestion. Anaerobic digestion is exclusively used to, let's say degrade carbon, okay? And big molecules typically not nowadays. So what you mentioned is typically what is called activated sludge processes. Mm-hmm. And I know in that case, but for me this is not an issue fundamentally, because typically the people tend to organize the degradation in steps. So you have anoxic and aerobic phases when you do different things. So let's say nitrogen transformation, denitrification, nitrification, and so on. And so then in that case, this issue is still is working well, and the time constant, the fast time constant is only for oxygen, but the oxygen is not an issue because you are able to control oxygen quite well today. So with that respect, this is not an issue. Probably an issue is probably with phosphate. That's a different, that's for sure. That's phosphate. Phosphate is still difficult. Yet, the problem today with nitrogen is nitrite. Okay, so the problem is nitrites. You tend to let's say nitrite is an intermediate. You know that. You have let's say ammonium, nitrite, nitrate, and typically the problem is the intermediate. Typically, in that case, and it's not completely solved. Okay, so one of the projects on which I'm working today is, let's say. It's called Mokope, and it's typically the treatment of wastewater of Paris and its suburbs. And so typically they have problems when they have what they call, let's say, extreme events like big storms and things like that. So typically in that case, it happens that they can go up over, let's say, the norms in that case. And typically nitrite typically is the issue. Okay. And on top of that, for me, the issue of let's say this municipal wastewater treatment plants is, let's say, what we call the micro, let's say, pollutants, which is something which is quite difficult to handle today. But this is another story. There's a lot to say about that.
Without neglecting the small number of measurements and instruments that you have there.
In that case, it's impossible to measure them because it's trace. It's not concentration. It's traces. But you know what trace is. So typically, concentration you can have what we call, I would say, milligram per liter. This is standard. But in that case, traces is very, very small. Let's say concentration and it's very difficult to measure. And that's a big issue today.
And that is my second question is, how would you sell to chemical engineers, to design engineers, the relevance or how important control and knowing the models is? Because usually you have many steps along the design of a chemical plant or a chemical process. Conceptual design, basic engineering, detail engineering, and at the end we end up with this P and ID instrumentation, pipes and instrumentation diagrams that they come with the closed loops, with all the instruments, but for basic control, for PIDs and perhaps on-off or something about related to optimization perhaps, as you said, RTO, but they are so rigid that you cannot modify the control policies and the control loops. So how would you sell this to the engineers designing the plan, saying that it's important to design along with how to control the plant in the future?
Okay. For me, the issue in the chemical and the biochemical industry today is the fact that you have more and more, you have no more, let's say, steady state operation. This is something that is not let's say, the case in so many applications in practice. And so the issue is to know the dynamics. And for me, it's a question of education. So first year in engineering, there should be a course of dynamical systems. So people have to understand that the fundamental is the fact that you have to understand that you have systems that are changing with time. And then the rest will follow for me. But this is a problem of education. Still today, and this is typical in chemical engineering, any reactor design course is based on steady state models. That's crazy. That's just crazy. How can you convince people from industry that control is important? Control is related to the fact that you have to deal with dynamical systems because the systems are in dynamical situation. Even when you have a disturbance, when a disturbance comes into the system, this makes the system become, in dynamic situation. And that's where it's so important. Control is so important. But the difficulty, for me, is a question of, control. Engineers have a mind that is related to steady state, to equilibrium. But equilibrium is just a specific case, a very specific case. Maybe an objective, but it's a specific case. For me, the main issue is education.
There was a question from Michel, I've seen.
So thank you for the talk, Denis. I was wondering when you spoke about adaptive control, not the extremum seeking case, but the other one, you didn't mention anything about persistency of excitation or what sort of excitation. So where is it hidden? Is it hidden somewhere?
Maybe I should. It happens that when you have a simple controller, the notion of I didn't put. I should have. Let's say the Lyapunov function in that case. And I see, in many cases, if you end up with a very simple controller, okay, since it is nonlinear. Let's say the regressor, so which has to be let's say the source of excitation, the regressor, is a nonlinear term, and the fact that it is different from zero is enough to guarantee, let's say, the persistence of excitation condition. in this case. And in other case, the fact that the system is changing with time, then if you have two, typically you can see that these two regressors are inherently, let's say, changing this time differently, so which guarantees the persistence of excitation. It's very specific. So in that case, it's very specific to the fact that we use the knowledge of the system in that case. And I don't hide anything. This is, yeah, it may look hidden, but it is not the case.
I don't claim you are hiding something, but
no,
it was
no,
just
no,
a matter of speaking.
No, but that's the main issue. I mean, that's why adaptive control failed to be, let's say, widely used in industry because of that. Because in many instances, let's say, people use linear controller and it end up with controller that do not, they cannot converge, and they have explosion of the closed loop system.
Thanks. So I'm from a completely different field, so it's interesting to see your presentation, but I'm not sure if I follow everything. But one thing that struck me is that throughout you seem to assume well mixedness of the systems that you're looking at, so that the concentrations can be described by a single variable, that is a scalar variable. In sort of my field, sometimes we've moved away from this kind of sort of like pretty equations to go more to simulations that are more individual based, because that well-mixedness assumption is violated. And I'm just curious whether that's whether you've sometimes felt the need also to move away from that.
So
that,
it's a personal
assumption.
it's a personal decision to make a presentation considering only homogeneous systems. But I worked a lot on what is called distributed parameter systems, PDEs, which are so very largely used in let's say, in reaction system, chemical engineering, for instance. It happens that I have a book that will come out, let's say, these days on that topic. So, of course, then in that case, then and I know how to handle typically, I mean, of course, it's more complex than what I've shown here.
Sure.
But of course, there are many ways to extend, let's say, what I said to cases where I don't have, I clearly don't have homogeneous condition.
And with how much of this framework then carries over to the
typically
to
the dynamical model,
case?
the general dynamical model that I mentioned before is typically the same, except that in terms of having what I call the dilution term, I will have a term which is related to diffusion and one is related to convection, typically. And then, of course, I mean, of course, this is a major source of differences, and then, you know, you don't have the same systems either. I mean, so you don't have, but typically, for instance, my reaction invariant property applies directly to this kind of system, even if it's not homogeneous, for instance.
Great, thank you.
So that's, you know, I mean, but, you know, I agree, it was a really a personal decision to just concentrate on that. It's sufficiently complex to explain what I tried to explain.
Okay, so I would propose to thank once again Denis for the very nice presentation and the very nice discussion, and to end here the first part of of our seminar series. So let's have an applause for Denis.
Thank you.
So, if you can leave me. So, as usual, we will get a pause of 15 minutes to have a coffee and start chatting. For those of you online, please be patient for 15 minutes, and then we will have our second talk. So, see you later.
Okay, so welcome back to our second talk of today. So the second talk will be from Professor Michel Kinnaert from ULB. Now, Michel, I know him since 15 years now because he's the director of the SAS, of the department where I work in. I could say a lot of things about Michel, in the sense that, all these years I could appreciate really the huge amount of very interesting work that he has done in different fields. And on the other side, on the personal side, also the fantastic person he is. So I'm very happy to present him and to leave him the stage.
Thank you, Emanuele, for a nice introduction. So the title of my talk is some tips about the design of fault diagnosis system, and I will speak about 2 case studies. So to motivate fault diagnosis systems or health monitoring systems, here are just 2 examples of catastrophic failures. So wind turbines can be subject to fires. Here is an example. So these can have different causes, either electrical causes like short circuits or ignition of hydraulic oil. And that's the first example. Another example is the accident that took place on the Qantas flight from London to Sydney quite some time ago. And so what happened is that shortly after taking off from Singapore, the reactor was subject to severe damage, and the damage of this engine was investigated, and it was seen that it was caused by an excessive leak of oil, and despite the high leak of oil, it was undetected by the monitoring system of the airplane. So that brings me to the goal of and the motivation for the development of performance health monitoring or fault diagnosis system. So what we aim at is the early detection and localization of degradations in order to be able to achieve predictive maintenance. So a synonymous that I will use for localization is isolation, and the degradations will be also called faults here. And I will give you some examples of faults later on. So the objective is that if we have a state of health indicator of our system, we can perform remedial actions before these catastrophic failures occur. And it also allows limiting the maintenance costs because predictive maintenance will typically be much less costly than corrective or preventive maintenance. It also allows us to keep nominal performance levels for our process or device, and so probably save energy or avoid possible environmental impacts, negative environmental impact. And also we are able to avoid costly unexpected shutdowns. So what are some examples of faults? Here are a few possibilities. Sensor bias or drift, abnormal friction in gears and bearings, abnormal backlash, intern short circuits in electric motors windings. This can be due to the degradation of the insulation, a leak in a tank or a pipe, battery overheating due to increased internal resistance, and so on and so on. So a typical fault diagnosis system is structured in the way presented here. So here you have on the top the supervised system, which can be an electric motor, a wind turbine, and so on. And typically, this model is driven by some known inputs, which are the comments that you are sending to the actuators. And you have also a series of sensors that equip the device, and these provide what I call here measured outputs. This system is also subject to disturbances. If you think of a car, you will have wind gusts that can affect the speed of the car, or you will have a difference in the slope of the road. These are disturbances, so unknown, unmeasured signal that affect the behavior of your system. And the faults are also unknown. And so what we want to achieve is being able to detect and determine when the behavior of our system is not anymore normal from what is available, namely the known inputs and the measured outputs. And so the diagnostic system, which is what is here below, is made of typically two parts. The residual generator. So a residual is simply a fault indicator. It's a signal that will nominally be close to zero, and that will take significantly non-zero values upon occurrence of a fault. And then you have the decision system. The decision system will analyze the pattern of zero and non-zero residuals, and from then decide which is the most likely fault and possibly estimate a fault magnitude. So I will illustrate through two case studies some issues in the design of our diagnosis system. And I will in particular show you that with quite simple models, we can already achieve quite effective results. So the first case study is the monitoring of electromechanical actuators for aerospace and aeronautical applications. And this is ongoing work with Louise Massager. We are working in collaboration with SAPCA, and we have a specialist in electric motors, Geoffrey Postal, from the BrIAS department, who also give us some help. So what is the motivation? Well, we are looking at two types of applications. One is the case of reusable launchers or simply launchers. So the orientation of the nozzle in those launchers and for the future reusable launchers, the deployment of the legs of the launcher, these things are actuated by these electromechanical actuators, which we denote in short EMAs. And of course, we have to ensure the proper reliability of these actuators, and to ensure this, we monitor the state of health of these actuators through the flight, and also for reusable launchers in between flight. But we have to evaluate the state of health of these actuators without dismantling them and putting them on test experimental setups. And we have to leave them in place and from the available data deduce what is the state of health of these actuators. Another application is the movement towards more electric aircrafts. Presently or formerly, a lot of primary control surfaces of the airplanes were equipped and actuated by hydraulic actuators. And the trend is to move from these hydraulic actuators to electromechanical actuators. It has several advantages. The removal of the hydraulic circuits limits the weight of the plane. It also avoids using hydraulic fluids which are
far from nice from the environmental perspective. So these are two main issues, and that's why the movement is in that direction. But to equip such critical control surfaces, these EMAs must be equipped or must be equipped with health monitoring system to guarantee the appropriate level of reliability. And so that's a second motivation for the use of such actuators. So looking a bit more carefully at these electromechanical actuators, here is the way they are composed. So they have mostly an electric motor, which is a permanent magnet synchronous motor in the case we will consider. And this motor is driving a gearbox and a ball screw mechanism that induces this movement of the rod here. There is a suitable power electronics that ensures the control of the motor. So in here we will focus on electrical and sensor faults, and one of the difficulties is that we are working in closed loop here, so that the impact of the faults is more difficult to understand, at least from the intuitive point of view. So I will not bother you too much with electric motors, but just to tell you that we consider a star-connected with motor with insulated neutral point. And we consider a situation where a sinusoidal flux is induced by the permanent magnets of the rotor. And so one of the sort of faults that we will consider is short inter-turn short circuits between within a coil. So that's due to the fact that the winding is made of turns, and the coil is surrounded by an insulator, but this insulator can be destroyed as time evolves, and that causes then short circuits between some turns of the coil. Another possible fault is the increase of the resistance of a coil due to the fact that when there is an overheating, the section of the coil could decrease. So what is the typical pattern of the current within such a machine? Well, in healthy situation, you have actually three-phase balanced three-phase signals, and that's what you can see here. So all currents have the same magnitude, and they are shifted apart by 120 degrees. But when there is a fault, and here I consider especially exaggerated fault levels in such a way that you see what is the impact of the fault on the signals. These signals are generated from a digital twin of our EMA. So when there is inter-turn faults, and 10% of the coil is subject to such faults, you get this stored signal. And this is what you get when there is an increase in the phase resistance. And so what you see is that the magnitude of the three signals is not anymore the same on the one hand. And on the other hand, given the properties of the motor that I have told you, the sum of the three currents must still be equal to 0. And to achieve this, there is a phase shift which is not anymore equal to 120 degrees between these different signals. if you look now at sensor faults, we consider here two kind of faults. So a change in gain of the sensors or an offset in one of the sensors. And due again to the control scheme, these faults affect all three current measurements. And what you see here again is that a change in gain means that the amplitude of the different measurements is not anymore the same. And an offset induces a change in the mean of the currents. But in this case, the sum of the currents of the measurements is not anymore equal to 0. What is still equal to 0 is the sum of the actual currents. But the measurements are not the actual currents due to the sensor faults. So we see that we can actually model these current signals independently without the need to model the motor itself. And that's what we are going to do to try to achieve full diagnosis. The advantage of doing so is that we will not need to know the parameters, the resistance, the inductance of the motor, which can be subject to temperature changes. And so this brings uncertainty. Here we stick to the measurement of the current. So a three-phase, balanced three-phase system can be represented in this way. And you can show that these three sine waves can be actually generated by a simple two-state system, so a system of two linear differential equations, which is an oscillator. This oscillator will generate in its states a sine wave and a cosine. And if you add up this sine and this cosine and multiply them by proper values, you get this balanced three-phase signal. So this is for the healthy situation. For the faulty situation, what happens is that the signal magnitudes are different and you introduce a phase shift. So if we take as reference the first signal here, we can actually introduce four variables, which are MB over MA, MC over MA, and the respective phase shift with respect to phase A here. So that makes four unknowns. But if we consider first the case where we have interturn short circuits or increase in resistance, we have seen that Kirchhoff's laws then must hold. And if Kirchhoff's laws hold, that's introducing an extra constraint, which means that these four variables can actually be expressed in terms of two independent parameters, which we denote psi1 and psi2 here. And so that means that in the case of winding faults, our model takes this form where the only thing that changes is the equation that generates the three currents from the states. And this is a simple diagonal matrix where we have these two unknown parameters, and the C matrix is becoming C tilde, so this C matrix is changed a bit as well. In the faulty case where we have sensor faults, well, we have seen that bias or an offset induces a change in the mean, which we can characterize in this way, so simply an additive constant in each line of my equation that gives the current. And the gain change is simply modeled by this diagonal matrix, which again will multiply each measured output. So notice that these faulty models also contain the healthy models for some values of psi1 and psi2 Namely, here, if I take psi1 and psi2 equal to 1, I will recover the healthy model here as well. And here, if I take them equal to 0, I will recover the model as well, the healthy model as well. So we have to keep that in mind for a later stage. So this brings us to the design of the online fault diagnosis system. So the equations that I've just written down, I can formalize them a bit more and discretize them. So as we have seen, in the faulty case, there are some parameters that are introduced here. These parameters do not change very fast, and so we can consider that somehow when we have recorded data, the parameters are quasi-constant with respect to the dynamics of the sine wave that we are considering. And so that's what we are saying here. Our parameters are quasi-constant, but they are uncertain, and this is represented by adding noises here. This is the standard form for this output equation here. And what we have also introduced is that the current signals are subject to noise, and we have represented noise, measurement noise here by V. So these noises can be characterized by the so-called covariance matrix indicated here. And so now the problem is to determine in what situation our motor is working. And so to this end, we want to estimate the parameters here and determine in what sort of model, what is the most likely model among the models we have been considering previously. So we have this model, this model, this model, plus the healthy model, which is the one that fits the data best. And so to achieve this goal, we will resort to what is classical in control engineering, namely state observers. And here, as we are in a stochastic framework, we will resort to what is called a Kalman filter. A Kalman filter, if I had a linear model, would yield the minimum variance estimator. Here, as I'm in a nonlinear case, I look for an approximate solution, which is given by the extended Kalman filter. So this extended Kalman filter will take as input, something I forgot to say up to now, is that I assume that my motor is operating at constant speed. And omega E here is what is called the electrical speed of the motor. It's linked to the mechanical speed of the motor thanks to the number of pole pairs of my motor, but this is a bit technical. So I assume that this electrical speed is constant, otherwise I would not have current that keep having the same frequency. And for the application that I consider, there are at least some times where such an operating mode is encountered. So I have my speed of my motor, I have my measurement of the current, and what I will generate is thus an estimate of the unknown parameters in my model. But I will also have an indicator of the quality of my estimate through what is called the innovation signal. So the innovation signal is simply the difference between the measurements and the prediction of my measurements from the previous data. So this is the prediction of my current at time k, given all the available measurements up to time k minus 1. And so it's called innovation because it's the new information brought by the measurements k. And so it turns out that these quantities have specific statistical properties that are estimated by the Kalman filter through what is called the covariance matrix of the innovation signal and the covariance matrix of the parameter estimate. And so what we will do is run different state estimators, one for each specific situation. So we will have one Kalman filter for the healthy model and 3 extended Kalman filter, or here it's dual extended Kalman filter, but I will not enter into the subtleties, for each of the type of faults. And then from the innovation, we are able to determine what is the relative likelihood of each model. And so, for instance, in this case, we are starting from a healthy situation and the fault in the, so we are initializing our likelihood to the healthy case. And then we are seeing that the likelihood for the winding fault is appearing because the data correspond to a winding fault. And we can check from the parameter estimates that indeed the parameter estimate and including surrounded by the confidence interval. So these parameter estimates do not include the healthy situation. So we can confirm indeed that in this example, we have a winding fault. So that's the principle of the fault diagnosis system we are looking at for the moment. And some preliminary results have been obtained on synthetic data, where 16 scenarios have been considered. The healthy case, different in-turn short-circuit faults with some, here you see that we have a much lower level of short-circuited turns. We have also considered a situation which I have not spoken about yet. It's interface short faults. So rise in phase resistance, gain change, and offset in the current sensors. And you see here some results depending on the signal-to-noise ratio of our current signals. You have here the probability of misdetection, PMD. The probability of false alarms, so then an alarm is generated while the motor is in healthy case. And the probability of misclassification, so that's a situation where one fault is considered, the identified fault is not the correct one. So you see that the performance seem to be reasonable at this stage. And these results are obtained by performing 100 realizations for each of the 16 scenarios with different noise. So what changes is the noise realization. So what's the difference between the synthetic case and the actual signals? Well, when you look at actual current measurements, and Geoffrey Postal gave us some of them, what happens is that you just don't have one sine wave. Okay, these signals are made of several harmonics, and here is actually the Fourier transform of one such signal. And you can see that there is actually a fundamental here around 50 Hertz. And then you see harmonic 3, 5, 7, and 11 here, plus some other frequencies that are linked to nonlinear phenomena in the motor. So how can we cope with that? Well, the method I've just presented can be extended by just adding 2 more states per harmonics and modifying the output equation appropriately, but the global methodology carries over. And this is actually what the currents look like. So you see that you don't have any more this very pure sine wave. So here is the first results obtained by Louise on these experimental data. These data are for the moment obtained in open loop, not in closed loop, so we still have some work to do. And this is what we call the confusion matrix. So what you have here is the true class, so we distinguish healthy motor fault, sensor gain fault. We have not considered sensor offset here. And here you have the decision on, the decision taken by the diagnosis system. And you see that, so here we consider all the data that Geoffrey has provided us with. And what he did is he modified the load of the motor so that we have different signal-to-noise ratios in our data. And you see that if we consider all signals-to-noise ratio, we get some indeed erroneous decisions. Like for instance here, you have 13 situations where, despite the fact that you have a motor fault, it's declared to be healthy. So this is missed detection. You have also here 1 false alarm, but you see that in the majority of the cases, a correct decision is taken. If you have increased signal-to-noise ratio, you have even better results. So what is the main message to take from this first example? By analyzing and understanding the effect of the faults on the measurements, we were able to use simple signal models and to avoid using a model of the motor for which we need to estimate parameters that could be varying with temperature, for instance. So ongoing work is to look at real data in closed loop, systematic tuning of the extended Kalman filter, and possibly also constrained parameter estimation, because indeed here we have to go in these 2 steps where we check that the parameter estimate does not embed the healthy case. Another approach could be to make sure that this estimator will never estimate the healthy case by enforcing that the parameters stick to some situation where the model is faulty. So that was for my first case study. So please stop me if I'm too long. The second part of my talk will be dedicated to wind turbine monitoring. And so I will have 3 sections, but the last 2 are very short. So I will start with the issue of loss of performance detection, and then I will go to generator cooling system monitoring and give a few hints on a global monitoring system. So here is a very quick look at what a wind turbine looks like. So you have here the 3 blades of your turbine. You have what is called the low-speed shaft that drives a gearbox. You have the high-speed shaft that is connected to the generator producing electricity. Now what I want to stress here are the 3 types of actuation mechanism on this wind turbine, 3 main types. So you have the pitch. So the pitch allows you to orientate the blades. You have the yaw drive. The yaw drive is here schematically indicated by this. So it allows you to orientate the nacelle of your turbine in such a way that normally the nacelle should face the wind to extract the most of energy from the wind. And finally, you have the generator torque. So you can somehow try, thanks to the power electronics, control the torque of the generator in such a way that you control the rotational speed of the generator and the wind turbine. And the reason you do this is explained through this graph, which is called the power curve of the wind turbine. So here you have on the y-axis the power produced by the wind turbine, and on the x-axis the wind speed. And you see that there are actually 4 zones. Below a certain wind velocity, the energy in the wind is not sufficient to be able to produce electricity. So this minimum wind speed is called the cut-in wind speed. And then you have what is called the maximum power point tracking zone, which is this zone. And on onshore wind turbine, this is the zone where the turbine operates most often. So in this zone, you are actually controlling the speed of the wind turbine in such a way that you extract the most energy from the wind. That's why it's called maximum power point tracking. Then you reach the rated power, which is called Pn here for nominal, at the nominal velocity. And finally, and this depends on the wind turbine, this 4th zone, you don't have it necessarily. You have sometimes what is called the soft storm transition zone, where above a certain wind speed, the power generated is decreased before cut off, and so stopping the turbine when there is just too much wind. So this is the steady state characteristics somehow of our wind turbine. And this is what you find in the data sheet of the wind turbine. But in practice, all you have available are data points, and these data points come from SCADA data. And these SCADA data are typically 10 minutes average of notably the power, the wind speed, and a series of other signals like the pitch signal and so on. So here we will choose to try to monitor our wind turbines using this power curve as we expect, so for a given average wind speed to produce a given average power. Now, what should we take care of? Well, one first thing is that the produced power, available in the wind for a given wind speed also depends on the air density rho here, and A here is the area swept by the blades. So we have to normalize our power curve by rho properly in such a way that we can compare the power produced in different days where the density is different. So there are different ways to do that. You must also account for the way the wind turbine is controlled. We have chosen this one, and just for the sake of clarity here, what you just need to keep in mind is that the normalized values are indicated by this 0 exponent here. Now, when you have normalized the data, here is what you can get when you try to use SCADA data and plot the power curve. So you see that besides the curve that you have in the data sheet, you have some additional points. You have some dispersions because you are doing also 10-minute average. But you have clearly situations where, for instance, here the wind turbine is at standstill while it could produce. Mainly, it could be in maintenance, for instance. You have situations where it is operating in power derating mode. That means that the grids cannot accept all the power available in the wind, and so the wind turbine is derated. And you have points like 3, for instance, which corresponds to high-speed startup. So these operating conditions are different from normal operation, and so we should discard them to have a monitoring system that covers most of the operating cases. And what is our aim? Our aim is to detect certain malfunction in our wind turbine. A possible malfunction is what we call yaw misalignment. In yaw misalignment, what happens is that the nacelle is not facing the wind anymore. There is a misalignment, so an angle here, gamma, which is non-zero. And this yaw misalignment induces a reduction in the produced power of the turbine. To show this, this is an experimental curve and the little triangles here obtained for a 75 kilowatt wind turbine, experimental wind turbine. And so you see that indeed with a non-zero yaw angle, the produced power is decreased. So what is the problem we aim to solve? We want to monitor the performance of the wind turbine and detect degradation such as yaw misalignment, for instance. And we need to account for the outliers in the design. So we will operate in the following 2 steps. First, residual generation, then decision system, and we will end up with a validation on real data. So actually, these are already real data, but we will validate with real data corresponding to 40 operation. So again, we will try to use very simple models. And as we are control engineers, if you flip the power curve here, and keep in mind that we are essentially interested in this operating zone, which is the zone 2, which corresponds to the maximum power point tracking zone. So if you flip this curve, you see a curve which is very similar to the step response of a typical second-order model. And so that's what we have been using to parameterize the curve linking the normalized power to the normalized wind speed. And so now we must get rid of all these outliers. To do this, in statistics, it's classical to use iterative reweighted least squares. That means that initially one will solve a problem, a least squares problem. So we will sum here over all the samples the square of the errors between the measured power and the estimated power from the model. And at first, we will start with a weight which is equal to 1. And then we will compute for each data point the error. And we will introduce a weight which has this shape here. So when the error is above a certain threshold, the corresponding data in the optimization problem is weighted less. And we iterate the determination of the parameters, so the solution of this optimization problem, until there is a small difference between 2 successive iterations. And this is the type of result we get. So you see that the weight corresponds to the color map here. So you see that indeed the points that are weighted the most indeed correspond to our power curve, and the outliers have very low weight and do not significantly affect the parameters of our curve. Now we have our model of our power curve. Let's look at how well it fits when we are using actual wind turbine data. So we have used here wind turbine data coming from 2 wind farms that are called SPDM and CBAR respectively. And so you see that the errors match quite well a Laplace probability density function. So these are normalized histograms. And so we will characterize these modeling errors by Laplace distribution. And now the idea is to try to see what is the impact of a fault. And here, remember, we look at Yau misalignment. What is the impact of a fault on this error distribution? Can the distribution be used to characterize the presence of the fault or not? So here, as it's difficult to have faulty data on which we have sufficient control, we have used a realistic wind turbine simulator developed by General. It's called Aerodyn Fast, and we have simulated 10-degree yaw misalignment. And the blue dots corresponds to the faulty turbine, and you see that the deviation from the normal, the healthy turbine, essentially occur in zone 2, and in the fast storm, the soft storm transition zone. But as we are operating very seldom in this zone, we will discard it and focus on this zone. And this is the modeling error that is obtained upon occurrence of this yaw misalignment fault. So you see that there is a mean shift in the Laplace distribution, so that we could indeed detect a shift in the mean. In the healthy case, our Laplace distribution will have a mean very close to 0. In the faulty case, it will be shifted. And so our decision system can be based on the log likelihood ratio, or the likelihood ratio between the healthy and the faulty probability density functions. So more precisely, if you consider the modeling error, which we call R here for residual, or for a given time horizon, and if you consider that these samples are independent, you can easily compute the likelihood function in the presence of the fault and the absence of the fault. And a standard test consists in comparing this likelihood ratio to a threshold. And if the likelihood ratio is below the threshold, it's the healthy case that dominates. If it's above, it's the faulty case that dominates. And this threshold must be adjusted to ensure that the probability of false alarm is appropriate. And this is an example of what we obtained with real wind turbine data. So what you see here is the produced power of the turbine over the years. And here is the indicator. So notice that we built an indicator each time after a few weeks of data, because we must be able to reconstruct the power curve or to estimate the probability density function with sufficient precision. And you see that at some stage we cross actually the 0 threshold here, which corresponds to the occurrence of a fault, and indeed a yaw malfunction was obtained at this stage. So a maintenance operation took place, and you see that our fault indicators falls back with 2 negative values, which then correspond indeed to, again, a healthy situation. So just a few more words, speaking about generator cooling system monitoring. So here we speak about the cooling system of the generator in a wind turbine. So this cooling system is actuated, or is made of fans. There is actually a series of 3 fans, and there are temperature sensors in the coils of the generator, and there are actually 3 coils and 3 temperature sensors. And what we have been able to show is that, again, using a very simple dynamic model, first order dynamic model actually, one for the cooling of the coils, so when the cooling system is operational, one for the heating of the coils when the cooling system is not operational, because this cooling system works in on-off mode. Well, when just keeping this very simple model and using, again, simple statistical tools, we were able to obtain a for diagnosis system that has reasonable performance, or at least that has some interesting properties as compared to what the SCADA system of the wind farm is doing. So we have here a series of 43 wind turbines and data recorded over 3 years. And so what you see here with the yellow dots correspond to SCADA alarm. And the red dots correspond to work orders, so maintenance operations. And on the other hand, the new monitoring system that is based on the dynamic model is issuing a green information when the wind turbine is healthy. A red line means alarm, and a blue line means warning. And what you can see is that most SCADA alarms occur in autumn or late summer. Why? Well, because this is the period of the year where the temperatures are still reasonably high and there is significant wind. So if you have a monitoring system that just compares the measured temperature to a threshold, that's when it will be triggered. But as you can see, for instance, in here, our monitoring system has detected a fault way before the first alarm takes place. And this is simply due to the fact that it detects that the cooling dynamics is not what it should be, so that a fan is probably faulty already by then. And so that shows you that by using simple dynamic model, you can already anticipate failures compared to what you have in traditional SCADA system quite long in advance in some cases. So this said, I think that I have given you a few elements, a few components for diagnostic system. The way I would see a global for diagnostic system, for instance, for a wind turbine, would be to have a series of such blocks that I have presented you, preceded by a systematic measurement validation. And as some of these blocks might be sensitive to, the same faults, there is a need also for gathering the information issued by these blocks inside of a global fault diagnosis system. And the objective would be to have plug-and-play models that you could introduce here in place of these 3 dots, and that you could have some systematic way to adapt this global fault decision system without redesigning it completely once you add a new device. So in conclusion, I hope I have shown you that it's possible to use reasonably simple models in fault diagnosis. You must be careful when you have real data to clean them properly, but there are ways to clean such data reasonably easily. Statistical approaches give you the possibility to detect relatively small faults. And I believe that we should aim at modular structures for diagnosis system. And finally, I think we should also aim at diagnostic system that can be tuned with relatively few data. It's not possible to wait, for instance, that a wind farm has been operating for 1 year before being able to start monitoring it. So thank you for your attention, and I'm open to questions.
So I imagine there will be questions.
Thank you. Thank you very much for the very nice talk. So I was curious. I think that the main message of all these approaches is that we need to rely on a model in order to do fault detection. I guess modeling takes efforts. We need to develop them, tune them, and then refine them over time. I wonder if there is a view towards moving to a framework where we only use data, statistical framework or something along those lines, or if there is a strong view to remain on a model-based approach.
So I think it's what is model-based and what is not model-based is a real discussion. I mean, because here, as you can see, I have a model, but I have a model of a sine wave, which is a signal. So is it model-based? Is it data-based? That could be discussed. And so I think what I would like to stress is that, yes, we can use model, but we can go with very simple model if we analyze the problem sufficiently. And what we should aim at is using models or methods that are as little dependent as possible to the operating mode of the system or some specific parameters of the system. So, we should definitely be aware of what physical phenomena could influence our model or data in such a way that we can account for them or take extra measurement to take them into account. So that's, I guess what's important is to analyze the physics behind the device we are looking at and not just stick to the data. I don't know if I answered your question or not.
Thank you for the presentation. I was wondering what happens when you have multiple faults that are happening at the same time. Are you able to distinguish between them, or yeah?
Okay, so yeah, that's a bit tricky. We could, in the first case, for instance, have models that include the two phenomena together, for instance, a sensor fault and a bias fault, and possibly estimate both cases. The more parameter you have, the the more difficult it is to estimate them independently. So you must be careful. There are rare situations where you can really build indicators that will only be dependent on one fault and just one fault. And in that case, of course, it's possible to achieve simultaneous fault detection and localizations. But it's not very often the case in real applications. And so still having the possibility to detect and isolate multiple faults, it's also a trade-off between the complexity of the fault diagnosis system you are building and the possibility to achieve this goal. I think also that most often faults will occur not synchronously but progressively, and so we could still have benefit of having a fault diagnosis system that only take each fault at a time.
Thank you.
Other questions? If not, actually, I have one comment, because you said something very interesting in the previous question. That is, it's not a matter of data, it's not a matter of model, it's a matter of knowledge of the process we are playing with. Mm-hmm. So somehow, in classical control, there are plenty of papers that basically say, and plenty of people that have said for decades, give me the equations and my theory is general for whatever thing that is behind the equations. And then when you face reality, we have seen in your talk, we've also seen the talk of Denis before, you must have a knowledge of the process you are controlling. Maybe this is also something that is true for everything that is data-based. One cannot think that the technique completely allows us to be independent from the knowledge of what we do.
Yes, I totally agree with you. I believe that we can, but if we can try to do something that does not exploit any physical knowledge. But I think the performance we will obtain with the end product, based on not knowing anything and discarding everything, will be much less ideal than what we can get if one exploits the physical insight that we have in the process. And for instance, here in the case that we have balanced signal, for instance, is a property that, if you take it into account, allows you to have much better performance than if you just discard that and start building robust observers. You will never get the same type of performance. So it's, for me, and that's why we are engineers. I mean, engineering is just exploiting physics and merging different fields. Otherwise, we are just too specialized. And I think when we start dealing with application, we must really also cooperate with the specialist of the applications to be able to exploit the most of it.
Other questions, comment? Well, then I will take the occasion to provoke a little bit another thing that was, again, a follow-up of something that Denis said, that is about instead the needs probably for engineering in general to have knowledge of dynamic system from the very beginning. Do you have the same feeling?
Definitely, yes. As you have seen, the dynamics here is everywhere. Okay, I have used a steady state characteristic for the wind turbine, but except from that, for the simple thermal process, we have used dynamics, and we have shown that taking into account dynamics makes a complete difference. And it's the same experience that we have encountered in many other applications. So I think dynamics is fundamental for control engineers, but more generally for any engineers. And indeed, I think it depends also on the training and the tradition. I would say that civil engineering and chemical engineering are traditionally disciplines in which the dynamics is not very much taught, while in some other engineering disciplines it's much more developed. So I guess it's also very culture dependent, but it's definitely very important to account for the dynamics, and that helps a lot for diagnosis also, because a fault induces a transient, so a fault necessarily is seen through dynamic phenomena.
Okay, so with this, I would thank again Michel. Thank you, Michel.
Thank you very much, Emanuele, and thank you all for listening.
And so with this, we will close here the formal part of our Thursday's meeting. I say the formal part because, as usual, the Thursday does not finish here, and you are more than welcome to stay longer with us, to have discussion around the coffee, to have crazy idea, brainstorm ideas, and see, and even just have a pleasant coffee with some pleasant people. So with this, we say goodbye to the people online, and we invite them to be again with us next Thursdays, and the same is for all of you that are present here. So see you for a coffee, and see also you for the next week. Have a good afternoon.